Hello everyone. As a crucial component of human social behaviors, gaze can express human attention explicitly. In this research, with the help of the RGB-D camera, we focus on inferring the person's gaze target in 3D scene. Novel datasets and deep learning architecture are introduced to solve this problem. We contribute two datasets. The RGB-D Attention dataset is rebuilt by using two activity datasets. These two datasets are collected by RGB-D cameras containing RGB and depth images. We construct color point clouds through these two types of images and camera parameters. Then we annotate the person's gaze target manually in the 3D point cloud. We have also extended the 2D GazeFollow dataset. Depth estimation method is introduced to generate estimated depth images. Considering that these 2D images are from the internet, we also provide estimated camera parameters. Then the 2D scenes and annotated gaze target can be transformed into the 3D space. The gaze vector space is to make full use of the 3D information related to gaze. We first construct a pixel space image. After obtaining the depth image registered with the RGB image, we add two channels to it to represent the pixel coordinates of the image. With the help of the pinhole camera model, the pixel space image can be projected into 3D space. We reproject all points in the 3D space into a 3-channel 3D space image. In this way, each pixel of the image can represent a point in the 3D space. We construct 3D vectors from the eyes to all points represented by the 3D space image. After normalization, the gaze vector space can be obtained. We propose a 3D GazeFollow model with 3 pathways. The first is a 3D gaze pathway used to extract features from the gaze vector space. The gaze vector output by the coarse-grained module is finally mapped to a heat map. This heat map is concatenated with the scene image and the head position mask, and then fed into the saliency pathway for extracting saliency features. The head pathway is designed to extract head features and form an attention map. These two pathways finally output saliency features with head attention. We design a dual branch prediction for our proposed model. After feeding the gaze vector feature, saliency feature, and head feature, the fine-grained module outputs the predicted gaze vector. This is a 3D gaze vector branch, and the cosine similarity loss is selected for regression. Another heat map branch selects saliency feature and head feature as input. After passing through the encoder-decoder architecture, this branch predicts a 2D gaze heat map. An L2 loss is selected for regression. We design a 2-stage training strategy for model training. In the first stage, the model is trained on the extended GazeFollow dataset. Considering that the 3D information in the dataset is obtained through estimation, the total loss is mainly L2 loss supplemented by cosine similarity loss. In the second stage, the model is trained on the RGB-D Attention dataset. This stage is initialized by the model parameters trained in the first stage, and the loss function focuses on both the cosine similarity loss and the L2 loss. After 2-stage training, the model can output the predicted 3D gaze vector and the predicted gaze heat map. We select a proposed 2D area based on the predicted heat map. The 2D area is projected into the 3D space to obtain the proposed 3D area. We assume that the person's gaze target exists in this area. In the area displayed in 3D Cartesian coordinates, only blue points need to be considered. In the vector set we built, it contains all the vectors from the eyes to these blue points. Then we select the vector most similar to the predicted gaze vector in the set. The brown point pointed by the selected vector is the inferred gaze target. In the 3D gaze following experiment, we gave some samples in 3D scenes. The red line represents the ground truth gaze, and the green line represents the predicted gaze. We also show the result of some samples on the gaze following dataset.